All right. Best test for determining whether an unknown compound is ionic or molecular is what? Which test told us 100% of the time? Conductivity tests. Okay. If something has a pH of less than 7, it's a... That should be an acid, but yeah. Okay, it's an acid. Number 3. You add a sample of an unknown compound to water, and the solution turns blue. What does it contain? Copper. All right. Now, we got to give the names of these compounds. So, for number 4, we've got calcium, which is a metal, and nitrate, which is a polyatomic ion. So we're looking at an ionic compound here. So in ionic compounds, we write the name of the metal, and then we write the name of the nonmetal. Since it's a polyatomic ion, we just write its name as it appears on the table. Calcium, nitrate. Okay, remember, we don't need any prefixes or anything because it's an ionic compound. All right, for number 5, and guys, today, no capitals. It's capitalized, it's wrong. Okay, we said that was going to be the way it was on Tuesday. Number 5, I've got silicone. Is silicone a metal or a nonmetal? It's a nonmetal. It's on the right-hand side of the staircase. Along with oxygen, so we're looking at a molecular compound, which means I do need prefixes now. So I'm looking at disilicone, okay, trioxide. Any questions on that one? Okay, for number 6, I've got lead, which is a metal, and I've got oxygen, which is a nonmetal, so I'm looking at an ionic compound. So we'll start out by writing lead oxide. However, if I look at lead on my periodic table, it has more than one possible charge. It can be 2 or 4. Right? We have to decide which one it is. So I look at oxygen. Oxygen's charge is always -2. So how many total negative charges do we have here? 4. All right, so if there's 4 negatives, there need to be 4 positives. And, okay, since there's only one lead here, it must have a 4 charge. So this is lead 4 oxide. Okay, and then for number 7, I've got a metal and a nonmetal, so we're looking at an ionic compound here. K is potassium. And P is phosphate, or phosphorus, so it's going to be phosphide, potassium phosphide. Questions on any of those? Yeah, I'll give them an electricity test, it's fine. No, it said 1 test. Okay, number 8. We need to put down the formulas here. So sulfur is a nonmetal, and there's a prefix in here, so we're looking at, obviously, a molecular compound. Sulfur's formula is S. Dichloride means, there's 2, SCl2. Okay, number 9, we've got a metal and a nonmetal. So for an ionic compound, we write the metal and its charge. Magnesium's charge is 2+. Okay, and phosphide, okay, big P, and its charge is -3. Now I have to drop and swap. All right, so the 2 goes over and down, and the 3 goes over and down, and we're looking at Mg3P2 for our formula. Okay, for number 10, we've got cobalt, Roman numeral 2, nitride. So cobalt is CO, and the Roman numeral tells me to use cobalt's 2+ charge when I drop and swap. Nitride is N, which is a -3. So drop and swap. 3 goes down and comes over. Okay, 2 goes down and comes over. And we're done. CO3, N2. And for number 11, sodium and carbonate. So sodium's a metal, so we treat this like an ionic compound because it is. Sodium is +1. Carbonate is CO3 from your table of polyatomic ions, and its charge is -2. All right, so when we drop and swap, the 1 goes there, but we don't write 1s, and the 2 goes here. Na2CO3. Questions on any of those? Okay, please give them a mark out of 11 and put it on the top. Let them see it, and then put it in the top box, please. All right, so in our lab, obviously we did solubility tests, okay, and we basically just said that solubility was how much something dissolved, which for all intents and purposes is true. Okay, that's what solubility describes, is the ability of one material to dissolve in something else. Most of the time that something else is water, all right, but it isn't always. Okay, water doesn't dissolve everything. Okay, some things are not soluble in water. For example, many forms of paint are not soluble in water, especially if they're oil-based paint, because oil is not soluble in water. Okay, that's why we use those things to coat other materials and protect them from the damaging effects of water. Okay, how would I get, let's say I was painting with oil-based paint and I get a bunch of it on my hands, because you always get some on your hands when you're painting. How do I get that off? Okay, soap and water might work if I'm willing to sit there with a stiff brush and scrub for a while. But remember, this stuff isn't soluble in water. Soap will help, but it might not get it all the way off, especially if it's oil-based stain. You have to use a special solvent. Okay, paint thinner. All right, Varsol, gasoline, if you really want to be brave. Okay, we'll remove those kinds of materials, because those materials are soluble in those other materials. So paint is soluble in paint thinner. That's why it's called paint thinner. Okay, gasoline, Varsol, okay, things like that. They're similar types of materials, so they're soluble in one another. That sort of makes sense? Yeah. Okay. So we want to learn some terminology related to solubility. Okay, we want to understand what's meant by the term polar molecule. And this one, guys, that's going to be big. We're going to come back to that a whole bunch of times in this unit as well as in the bio unit. Okay, water is a polar molecule, and since without water life can't exist, at least as far as we know, okay, polar molecules are pretty important. Okay, and then understand that because it's a polar molecule, water has many important and unique properties that make life on Earth possible, and we'll go into some of those during class today. Okay, and it's kind of explain how some of water's weird behaviors are explained by the fact it's polar and what being polar means. All right, some substances dissolve easily. Okay, we know that. Some things you put in water and they disappear almost right away. Okay, and others do not. Okay, this is solubility. All right, a substance is said to be insoluble if it will not dissolve in another substance. All right, if a substance remains insoluble in a solid form, we call it a precipitate. Okay, generally a precipitate is formed in a chemical reaction between two materials. Okay, this would be an example here in this picture, okay, where you mix two clear materials together and a powder forms out of nowhere, okay, and then falls to the bottom of the tube like rain falls from the sky, hence the name precipitate. It appears to just come out of the solution and fall to the bottom. Okay, everyone with me there? Yes? Okay. All right, so terminology here. A solution. Okay, a solution is any mixture containing a solute. That's usually the material being dissolved. It's often a solid, but not always. Okay, dissolved in a solvent, and the solvent is the thing doing the dissolving. So usually water. Okay, this is also known as a homogeneous or homogeneous mixture. Okay, what does the prefix homo mean? Keeping your minds out of the gutter, please. Same or one. Okay, same or one is what the prefix homo means. That's why you see it on homogenized products like peanut butter and milk and yogurt. All right, we want them homogenized so that they don't separate. Okay, if you take, like, let's say milk straight out of the cow and you leave it there, okay, it isn't homogenized. It will eventually separate, okay, into kind of the cream and the water, right? One will sit on top of the other. The same thing happens if you don't have homogenized peanut butter, right? If you buy peanut butter at a natural food store, it often isn't pasteurized and thus homogenized, and the peanut oil will rise to the top and sit on top of the rest of the material, right? And you always have to stir it, okay, before you can spread it on any food products. All right? So anything that is homogeneous has only one visible part. Okay? It is all one unit. It's all the same. Everyone follow me on that one? Okay. So this one here, this picture here on the left, is showing a homogeneous mixture or a solution. It is completely dissolved. We can't see any other parts. Whereas the mixture here on the right, okay, is what we call a heterogeneous mixture. Hetero means many. Right? So there are many parts to this material here. All right? And now, if I stir it, can I get the material that's sitting down here on the bottom to get suspended? But is that the same as being dissolved? No, because if it's suspended, it's eventually going to fall down to the bottom again. It's not truly one part like in a homogeneous mixture. Okay? We often call a homogeneous mixture a mechanical mixture. Mechanical meaning if I keep it moving, it looks like it's all one, but it will separate. Okay, is that kind of clear to everyone? Okay, so oil and water is a mechanical mixture. Okay, iron filings and sand is a mechanical mixture. Okay, because we can actually physically separate them. All right, with oil and water, if I just wait long enough, the oil sits on top and I can actually scoop it away. All right, with iron filings and sand, I just need a magnet. Stick a magnet in the sand, move it around a few times, and I've got all the iron on the magnet, and I've physically separated them. Okay, if I have a solid sitting inside a liquid that's not dissolved, I just need to run it through a paper filter, and I'll get the solid out. Okay, and have it removed. Or I boil off the water, okay, and I can leave it behind. Now that would work also with something dissolved. Okay? So we can separate them by a physical means. Everyone okay with that? Okay, so those are two important terms: homogeneous mixture, heterogeneous mixture, okay, solution, mechanical mixture. Okay, we need to understand what those are. Okay. Now, what about Italian salad dressing? Okay, is that a homogeneous mixture or a mechanical mixture? It's mechanical, right? Because it eventually all the kind of colorful stuff settles to the bottom. All the pieces of tomato and pepper and whatever else, they all settle to the bottom, and the oil rises to the top. You shake it up, okay? You get everything suspended, and you pour it on your salad. It's all good because it doesn't have time to separate, hopefully, before you eat it. All right? Chicken noodle soup, okay? Homogeneous or heterogeneous? Heterogeneous, right? I mean, the noodles don't, well, they might eventually dissolve, I suppose, if you left it long enough, but okay, they're solid parts, okay, in the soup, right? Whereas, let's say, if you had a can of pop, like Coke or Pepsi or whatever, okay, is that homogeneous or heterogeneous? Does it all look like one part? Yeah, it does. Okay. Now there are bubbles. I think that's what you're thinking of, right, Jacob? Okay, is you're thinking of the bubbles, but the bubbles are actually a sign that there is a gas dissolved in that material. Okay. Now the gas is coming out. Okay, so we do see that, but when it's in the can before you crack it, okay, the gas is trapped and actually dissolved in the material. Okay. If you shake it up, you increase the pressure, it comes out, and then yeah, when you pop the cap, it sprays everywhere. Okay. All right. Solute. Okay, solute is the thing being dissolved. Most of the time that's a solid, right? But it isn't always. Okay, we said yesterday that, or the day before yesterday, that alcohol dissolves in water. Okay, alcohol would be the solute because it's dissolving in water. Even though it's a liquid, it's still the thing that's getting dissolved. All right, so solute is the substance that is being dissolved. Okay, salt water salts the solute. Water is the solvent. Okay, so a solvent then is any substance that will dissolve another substance. Okay. Okay, water is what we call the universal solvent. It's kind of a misnomer because it doesn't dissolve everything, as the name universal would imply. Okay, but it dissolves enough things. All right. This is also why we call things like CLR and Mr. Clean and, you know, whatever kind of cleaners you have at home, okay, they're usually called solvents. Okay, they essentially, kind of a weird way to put it, but they make water wetter. Okay, they make it more able to dissolve other things, okay, like soap scum and hard water scales that might form on the inside of your bathtub or shower. All right, water by itself is not going to dissolve those. Okay, that's why they end up there and why they don't come off. But if you put some of this other stuff in the water, okay, you create a solvent that's stronger. Okay, and that is more able to dissolve other materials. Now, there's a bit of a chemical reaction usually between things like CLR and soap scum and things like that that enables them to turn into things that are soluble in water. Okay, and that's kind of how cleansers work. Questions on that? It's mostly just terminology, just stuff you got to memorize, guys. All right, so a precipitate, okay, is any solid which is produced in a reaction and will not dissolve in the solution. All right, so we've talked about precipitate already, but okay, in here we can see that okay, we've got a solid that's now settling to the bottom. Okay, and I'll show you. I think hopefully this link still works. Okay, a quick video of that. All right, now, like we said here, the definition for solubility, it's the degree to which a substance will dissolve in another substance. Okay, so simple definition there. And guys, usually when I'm giving you terminology, if I am going to test that, it's mostly like it would be like a multiple choice question, or it's just that I'm not really going to test it, but if you don't know what that word means, you might not understand another question that has that word in it. Okay, so that's what solubility means. Now, solubility can be affected by a number of factors. Okay? Those factors were things that we kept as controlled variables in our lab yesterday. One of the controlled variables you said was temperature. Okay? Because temperature affects solubility. Right? I used to drink lots and lots of Kool-Aid when I was a kid, okay? And I discovered a way to supersaturate the Kool-Aid. Okay? That is, make it so that it had as much sugar in it as possible. I would make it with hot water. Okay? Make the Kool-Aid with hot water. You can get way more sugar to dissolve in hot water than you can in cold water. Then I'd put it in the fridge, and as it cooled, the sugar would precipitate out and form a nice, beautiful layer on the bottom of the pitcher. That was when I knew I had perfect Kool-Aid. Okay? A sign of perfect Kool-Aid is solid sugar on the bottom. Okay? Because then you know the liquid suspended above it is saturated with sugar. It cannot hold any more. Okay? And then it tastes really good and rots your teeth and all those other bad things that refined sugar does to you. Okay? All right. Other things that can affect solubility. Movement. Obviously, we just subconsciously stir stuff when we mix things together because we know if we stir it, we can increase the rate at which it is absorbed and dissolved. Okay? Pressure can affect the solubility of gases in other gases. All right? Or in liquids as well. I think I have a video of that. I'm just going to show you that one. All right. Now, another thing. How many people like Twinkies? Okay, I'm going to ruin your life now. Okay, Twinkies, modern Twinkies, are soluble in water. That is, if you put them in a glass of water in short order, within like an hour, you will have a solution of Twinkie water. Okay? Now, a Twinkie is supposed to be cake. And the last time I checked, cake's not soluble in water. Real cake is not soluble in water because it's made from things that are natural, like eggs and oils and like fats, like lard and stuff like that. That's what you used to make cake out of back in the day, okay? Out of these natural ingredients. Well, the problem with natural ingredients is they go bad. So the shelf life of the original Twinkie was kind of short, okay? Because it would get moldy and bacteria would grow on it and then it would be spoiled and they couldn't sell it. So they said, that's no good. We have to find artificial replacements for the natural ingredients so that the shelf life of the Twinkie will be extended. So they started finding ways to replace the natural ingredients. Okay, eggs were replaced with an artificial substitute. Okay, this artificial substitute, incidentally, has the color of wallpaper paste. Okay, if you've ever seen what that looks like, or drywall. Okay, it's like gray. All right. So the problem with that is no one's going to buy a dusty gray-looking Twinkie. So they had to add something for color because eggs are yellow and the Twinkie wasn't yellow anymore. So they added yellow dye number 5. Yellow dye number 5 is a known carcinogen. That means it causes cancer. It's actually banned in many countries of the world by their Food and Drug Administrations. Okay, They also added preservatives. One of them is the same thing that's found in mortician's fluid. Yeah, keeps dead bodies from stinking. Okay? Also keeps mold and bacteria from growing in the Twinkie. Not so good. Okay? The oils were replaced by artificial ingredients, okay, and things like that. So we've got all these strange artificial ingredients that, incidentally, are soluble in water, including the stuff the filling is made out of. All right? The filling used to be made out of butter and sugar, because that's what frosting is made out of. Now it's made out of a bunch of other ingredients, okay, including sugar, but all of those ingredients will eventually dissolve in water. Okay? Original Twinkie, not water soluble. It would soak it up like a sponge and just expand to be the same size as the glass it was in. Okay? But this will actually physically dissolve. That's not a puddle of vomit, although what I'm talking about may cause one to form somewhere. Okay? But yeah, that is the Twinkie solution. Okay? That forms a little bit later. Right? Always a good idea to know what's in your food. All right, on the back of your periodic table, you have this. Okay, so if everyone can just take out their periodic table and have a look. This is a solubility chart. It allows you to figure out whether an ionic compound is soluble in water or not. Because some ionic compounds are actually not soluble in water. Most of them are, but some aren't. Okay? And some are less soluble than others. So, we can use this chart to figure it out. Along the top, you'll see that there's mostly negatively charged ions, with the exception of the first column here where we have hydrogen, sodium, and ammonium. Okay, but for the most part, okay, we're looking at negatively charged ions. Okay, and then down below we have two other rows. The first row says solubility greater or equal to 0.1 mole per liter. Essentially this means, whoops, sorry, I scribbled up the part I wanted to keep there. Okay, the first row is things that are very soluble. Okay, the second row, things that are essentially not soluble. Okay, very slightly means they hardly dissolve at all. So here's how I use this chart. Let's say I'm asked to find out whether this material, iron 2 fluoride, is soluble in water or not. Okay, so what I do is I go across the top looking for my nonmetal, okay, or my negatively charged part. So here it is. Here's where fluorine is. So I go down here and it says that fluorine is soluble with most things, which is about the least helpful thing a chart could say, right? Because what's in most? I don't know. Okay? If ever you see most, keep going, right? Go down and you'll find that there's a list below of things that fluorine is not soluble with. So if fluorine is with lithium, it'll form a what? What do we call the stuff that forms, starts with P? A precipitate. So lithium fluoride would form a precipitate. So would magnesium fluoride, calcium fluoride, strontium fluoride, barium fluoride, and iron 2 fluoride. Okay? So this material is not soluble according to this chart. Okay? If I had, let's say, this stuff. Okay, sodium carbonate. I do the same thing. I go across the top until I find carbonate. Here it is. Says it's soluble with, well, right there, soluble with sodium. Okay, so this stuff is soluble. All right, is that a pretty easy chart to use? If the pair is involved in the first row, it's soluble. If it's in the second row, it's not soluble. Pretty easy, right? Okay. You will be asked to use that solubility chart on both quizzes and unit exams, okay, as part of other questions. So please make sure that you know how to do that. We'll do a couple of practice ones here. Okay. I'm just going to write a few down here, and I want you guys to write next to them whether they are soluble or not. Okay, so let's have a look at these ones here. Okay, so for H2S, okay, so I go up here, I find S, okay, it's over on the far right hand side right here. It says, yeah, it's soluble with hydrogen. Okay, that one is soluble. Okay, potassium hydroxide. So I go along here, hydroxide's on the very end, and potassium is in the first row. All right, so that one is also soluble. Calcium sulfate. Okay, here's sulfate, soluble with most things. Calcium is not included in most things, so calcium sulfate is insoluble. And for number 4, lead 2 iodide. Okay, here's iodine, soluble with most things, but lead 2 is down here in the insoluble row. Okay, so that one is insoluble. Now, ammonium phosphate. All right, now I can look either way here. I've got phosphate right here, says it's soluble with ammonium, or I could go to ammonium and says soluble with most things, and phosphate's not listed down here in the insoluble row. Either way, that compound is soluble. Doesn't matter which one you looked at. Okay, you get the same result either way. All right, so that one is soluble. Okay, silver chloride. Here's chlorine. Okay, and there's silver, so that one is a precipitate. It's not soluble. Okay, ammonium nitrates. All right, ammonium is here, so is nitrate. They're side by side. It says soluble with most things. The other one's not listed down here, so that one has to be soluble. Whichever way I look at it. If I look at ammonium, it says soluble with most things, and I don't see nitrate here, or I look at nitrate, soluble with most things, I don't see ammonium down here. Either way, the result is the same. That's a soluble compound. In fact, there are very few nitrates that are not soluble. Okay, they're almost all soluble. And nickel 2 sulfide. So we go up here and we find sulfide. All right, it's not listed here in the soluble row, so it must be included under most and be insoluble. Pretty straightforward? Okay. Now, when we talked about ionic compounds and molecular compounds, we talked about how they bond to each other. All right? We have to review a little bit about how the molecular compounds bond to each other. We said when they bond, they don't trade electrons, they share them. Okay? Now that's an important thing to understand for us, because sharing for most of us implies some sort of equal amount of having the same thing. Okay? But for a polar molecule, it's more like sharing with a bully. Okay? When you share with a bully, are you really sharing? No, you have that thing like 1 out of every 8 days or whatever, okay, if you're sharing. Or if you're splitting a pizza, they get 9 of the 10 pieces, okay, that kind of stuff. Okay, that's kind of how polar sharing goes. Okay, polar is exactly as it would imply. There's a great difference between two places. All right, that's what polar means. So when we're looking at a water molecule, okay, we've got 2 hydrogen atoms. Each one has 1 proton and 1 electron. Okay, so here's the electron and here's the proton. And an oxygen atom that has 8 protons and 8 electrons. Now, when these two bond together, okay, the hydrogen's electron spends way more time down in this area, okay, and in fact even as far as to go this way around the oxygen atom sometimes, than it does up here. In fact, it's almost never out here, which ends up making, okay, the water molecule look kind of like Mickey Mouse, but with 2 protons sticking out the top. Is there anything more positive than a proton? No, it's the elementary positive particle. So if I'm looking at a molecule that's got 2 protons sticking out the top, it's like 2 big positives, okay, that are just exposed, okay, at the top of the molecule. Meanwhile, down here, I now have 10 electrons hanging out. So down here is going to seem pretty what? Negative, right? If electrons are negative and they're all hanging out down here, this is going to be the negative part, and this up here is going to be the positive part of the molecule. Okay? So it's polar because there's a positive side and a negative side. Just like the Earth is polar, it has a north and a south. Right? Does everyone understand what the term polar is kind of meaning there? Okay, so in a polar molecule, the electrons are shared, but they're not shared equally. Okay? All right. Now, if you look on your periodic table, one of the things that's on your periodic table is a term called electronegativity. So if you look up here on the key, okay, iron is the one that's up here in the key. It says atomic number is 26, and then right underneath that says electronegativity 1.8. So let's look over at oxygen. Oxygen's electronegativity is 3.4. Hydrogen's, by comparison, is 2.2. Electronegativity describes how well an atom can hold its electrons. The bigger that number, the harder it holds onto its electrons. So, because oxygen is so much more electronegative than hydrogen, it grabs hydrogen's electrons and holds them closer to itself than hydrogen does. Okay? And that's what leads to that unequal sharing of the electrons. All right, so the sharing's not equal. That's kind of the big thing we have to know about a polar molecule. Okay, it's polar because the electrons are not shared equally. Okay, and that's what this electronegativity means. Okay, so covalent bonds, that's the ones where they're sharing electrons. Okay, which electrons are unequally shared. Okay, are called polar covalent bonds. Here's what that leads to. If I've got a positive end and a negative end to a molecule, could it become attracted to other molecules that are also polar? Yeah, okay. The negative oxygen could be attracted to the hydrogens of other water molecules. Okay, and it is. How many people have ever seen or been able to fill a glass just slightly more than half full? Or sorry, slightly more than all the way full. And you get that kind of bubble or hump that forms over the top. Okay, it's called a meniscus. Okay, the reason that happens is because the oxygen, the negative end, the oxygen end of a water molecule actually forms a weak bond to the hydrogen atom of another water molecule. We call that a hydrogen bond because hydrogen's involved. Okay, when they bond like that, okay, they stick, and as a result, you get that meniscus that forms. All right, it's the same reason why water kind of makes bubbles on top of like the leaves of plants sometimes, or on a freshly waxed vehicle. Okay, things like that. You see water kind of make these beads. Okay, it forms these beads because of surface tension, and surface tension is caused by one water molecule bonding weakly with another. Okay, and I say weakly because if you get that thing filled just slightly more than full and you touch it, what happens? It spills up, right? You break that surface tension. The bond is strong enough to make that, but it's not strong enough to really hold it, all right? Especially not against any kind of major disruption. All right, so that's what we call hydrogen bonding, when we have a polar molecule that is attracted to another polar molecule and they form that weak bond. Now, those bonds break, but they also reform really, really easily. Okay. All right, so the water molecule is shaped kind of like a 90-degree angle. Okay, kind of like this. Okay, so about 90 degrees between the two hydrogens. Okay, and the unequal sharing makes them have positive and negative ends. Now, a water molecule, a single one, can bond, hydrogen bond, to 4 others. Okay, it can form one hydrogen bond here with its hydrogen, one hydrogen bond here with its hydrogen, and then oxygen is big enough that there's essentially 2 bonding points on it, okay, that are negative, that could bond with the hydrogen atoms of 2 other water molecules. Right? So if every water molecule can bond to 4 others, you can start getting kind of a intricate and fairly diverse network, okay, of this bonding. Okay, and that's what can create that surface tension. Right? Now, here's the problem though. Any substance, when you cool it, starts to do what? It starts to shrink, right? It starts to contract. Well, when it starts to contract, that means the molecules are getting just a little bit closer together. Well, there comes a point where you get this water molecule too close to this one, and the negatives start getting close to each other. And then what will they do? Like charges will repel. Okay, and so right at the instant before water kind of freezes, they get really close, and there's this kind of almost elastic repulsion action that happens right before the water freezes. And then as a result, ice expands. Okay, have you ever noticed that when you freeze water, it takes up more space? Okay, you've ever like seen a water bottle, if you throw it in the freezer, the bottom always pops out? Okay, because ice takes up more space than liquid water does, because just as those water molecules get close together, they get pushed apart and they actually take up more space than their liquid. Okay, that's incidentally why ice floats on liquid water. It's more dense. Water is one of the few things that does that. Most things, their solid form sinks in their liquid form. Can you imagine if lakes froze from the bottom? Okay, like it's just not something ice always floats in water. We don't. That's all we know. Okay, but ice is one of the few solids that's actually less dense than its liquid. Right? So yeah, it's kind of weird. Imagine if icebergs all sank, the Titanic would never have been a disaster. Okay, would have been just fine. All right. So you can see here, this is kind of a diagram of that. Okay, liquid water, the molecules are closer together than they are when it's a solid. Okay, so here in the ice, okay, the molecules look like this. They've repelled each other and formed a crystalline kind of state, okay, that we know as ice. Whereas in the liquid, right, they look like this and they're much closer together. All right. Has anyone ever done the thing where you throw the water in the freezer for a few hours, you pull it out and it's still liquid? Right? It's super cold, but it's still a liquid, and then you take the cap off to drink it, touches your lip and freezes? Okay, you can do that. I'll show you actually in one of the units here. I'll show you the video of that, and I'll do it for you. Okay, you can actually super cool water below 0 degrees, but it has to be very pure water. It won't work with like tap water. Okay, but if it's like RO or specially filtered or distilled water, okay, it can actually cool well below 0 without turning to a solid. Okay, and then all it needs is just one thing to start the crystallization process, and it flash freezes. Okay. I actually had a prof in university who did this. He brought in this container that had liquid nitrogen surrounding this pure water that was -30 and liquid. Right? And so he had it in this container. He pulled it out of the container and gently set it down, but he didn't set it down gently enough. And just setting it on the table caused a little bubble, and it flash froze and shattered the beaker. And he had just a block of ice sitting right there on the table, along with a bunch of broken glass. Okay, but you can do that. Okay, what he was going to do was he was going to take a grain of salt and drop it on there. Okay, because salt's a crystal, it would have acted as a seed crystal, would have caused it to flash freeze. But actually, just setting it down caused a little bubble to form. If you do that with a bottle of water, all you have to do is when you take it out of the freezer, turn it upside down, and as the bubble goes through the water, it'll freeze. Okay, or if you pound it on the table, it'll freeze. Okay, try it. If you got a bottle of water at home, throw it in the freezer. Okay, for let's say 5 or 6 hours. Pull it out, and if it's still liquid, bang it on the table, it'll freeze. Okay. Okay, so does everyone understand what these hydrogen bonds are all about? Okay, now we've said these hydrogen bonds they're not really strong. They're strong enough to support a few molecules, but not strong enough to support any significant amount of weight. Okay, so those hydrogen bonds, they form between water molecules, but they'll also form between water and other polar molecules. Okay, and this is how plants are actually able to draw water from their roots up to their leaves. Okay, they don't have any pumps. There's no pump in a plant like in the roots or anything that's pushing water up the plant. Okay, it's actually being pulled up by water evaporating on the leaves, and because water is bonded to itself with a hydrogen bond, they link up and they can actually pull the other water molecules up. Almost, if you ever played with like a barrel of monkeys when you're a kid, right? Okay, you link the arms together and you can pull up a whole bunch of them. That's kind of what goes on. Okay, inside the tiny little tubes that are in the trunk of a tree. Okay, the reason the tubes they have to be really, really tiny, like they're microscopic, because if they were a straw, there'd be too much weight and the hydrogen bonds wouldn't be strong enough to support the column of water. But if they're really, really small, okay, then it works. It's like if you try to drink through a really big straw versus a small straw. It's way easier to keep the liquid moving in a little straw. Obviously you get more volume through a big straw, okay, but it's easier to keep the liquid in a small straw than it is a big straw. All right. So in a plant, okay, here's what you've got going on. Okay, you've got two processes. One of them is called cohesion. Cohesion is hydrogen bonds between water molecules. Okay, so we need to know what cohesion is. Cohesion is due to the hydrogen bonds, okay, and it's between similar molecules. So water comes in through the roots of the tree down here. Okay, comes in like this. Each of these little gray dots represents a water molecule. Okay, in the tiny little tubes of the tree, okay, we can see that the water molecules are stuck together. So there's a string of 4 of them stuck together right here. Okay, blown up, that looks like this. Here's the hydrogen bond between these 2 water molecules. Okay, and they're all stuck together like that all the way up the tree, all the way to the leaves. So as one water molecule evaporates out of the leaf, it pulls all the others, just like links in a chain. Okay, so as it moves upwards, so do all the others attached to it. Now, in the trunk of the tree, the inside of those tubes is also polar. So the water molecules can form hydrogen bonds to the inside of the tube, okay, which allows them to not fall back down the tube, okay, when the pulling action stops, so they can stay kind of suspended in there. Right? That's what we call adhesion. Okay? Adhesion means to hydrogen bond with something different. Okay? That's why glue is called adhesive. It makes 2 things that are not the same stick together. Okay? So adhesion is 2 things that are different sticking together. All right. So adhesion, okay? All right, and you can see here surface tension. Okay, surface tension is related to cohesion, and it's a little bit related to adhesion as well. Right? If you've ever had like a really cold drink in a glass, and you see the condensation start to form on the outside of the glass, but the water droplet stuck to the glass, it doesn't slide down until it gets big enough. Okay, that's because it is hydrogen bonded to the glass. Right? And there's enough adhesion there to support, you know, a reasonably sized droplet of water. But as soon as that droplet of water gets a little bit too big, the hydrogen bonds aren't strong enough, they break, and that droplet of water slides down the side of the glass. Okay? Does that sort of make sense? All right? So it's important to understand those 2 terms, cohesion and adhesion. Okay? It's also important to know that a polar molecule doesn't share its electrons equally. Okay? That results in a positive end and a negative end that can attract each other and form those hydrogen bonds. Okay? So, unequal sharing of electrons, hydrogen bonds, cohesion, and adhesion. Those are the big 4 things we got to know about water being a polar molecule. Okay? All right. I've tried this time and time again. I've never been able to pull it off. Okay? But apparently, you can get a paper clip to sit on the meniscus of an overfilled glass of water. But after 45 minutes, I decided I had better things to do with my life. Okay? Apparently you can do it though. Okay? And you can see here, this was the droplets of water I was talking about, how they form that kind of that perfect sphere, but they stick to the leaf. Okay? Only when they get too big do they roll off of the leaf. Now, there's some animals that can also use this. Right? Sometimes you see bugs that can sit on the surface film, okay, of a lake or a stream or anything like that, right? And they seem to almost float on the water. Okay? Well, they're small enough that they don't break the surface tension. It's not that they're floating. They're actually sitting on the meniscus, the surface tension, the hydrogen bonded water. Okay? If you fly fish or anything like that, we use the same principle. Okay? You get it to sit on that surface tension without breaking it. All right? Just like a natural bug would. Okay? And it'll float down the stream. Or the Jesus lizard, okay, that can walk on the water. Right? Have you ever seen one of these things? Okay, now they look really clumsy when they're running, but like their legs are just going like this as they go across the water. Okay, but what they're doing is they're utilizing that surface tension. Now they can't stand on the water in one place; they'll fall in. But if they move fast enough, they can. As they break the surface tension, they can push a little bit with their feet and actually stay on top. They can't go very far because they start to slow down, and if you start to slow down, that's when things work out badly for you, okay, in terms of falling into the water. Okay. All right, so that's what we need to know about that. Okay, we've still got about 6 or 7 minutes, so take out those naming worksheets. Okay, Let's work on those a little bit, get some more practice. If you got questions, you got 5 or 6 minutes to ask, and you can come in and see me in scheduled help or at lunch today, okay, to get help on that naming stuff. So let's make sure that we do that.